Today we are going to start a new chapter. Chapter 2 is about graphing. Please take notes for this on the guided note sheets that you receive. The first thing I'd like to talk about is intercepts and symmetry. So today we are going to find intercepts for graphs of equations, and we're going to conduct a test for symmetry about the x-axis, the y-axis, and the origin. The most basic approach to graphing an equation is to pick x values and find the associated y values. So you can see that I've chosen several different x values and I've plugged it into my function. So I plugged -3 in and I got -3 squared is 9 minus 5 is 4. And from that I have a point I can plot. So I plotted -3, 4. So I'd like you to fill out the rest of this table. Press pause on your video. When you're ready to go on, press play again. Okay, so you can see that each of these points got plotted and then I connected them with a nice smooth line. And that is a graph of a parabola. The points where the graph crosses or touches either the x or the y-axis are called intercepts, and identifying these points helps us define the graph. The x-intercepts of a graph is a point where the graph intersects the x-axis at the x-coordinate. Now, what I want you to do is to cross off this next thing here. It says if the graph crosses an x-axis at 5, 0, then 5 is an x-intercept. That is not true. If it crosses, it is true, but I want you to think of the x-axis as a point. It's not a number. If the graph crosses the x-axis at 5, 0, then the intercept is 5, 0. Same kind of idea with the y-intercept. The y-intercept of a graph is a point where the graph intersects the y-axis. It's at the y-coordinate. Now you can see that I have drawn several examples of functions, and it says not all graphs have intercepts, and if they do have intercepts, they can have one or more of each type. So you can see that this graph has a y-intercept and it also has an x-intercept. The second graph has only a y-intercept. And the third graph has an x and a y-intercept that are the same. The point 0, 0 corresponds to both an x-intercept and a y-intercept. You may have more than one x-intercept, but you may only have one y-intercept. Now, to find x-intercepts algebraically, to find the x-intercept, you set the y value equal to 0 and you solve for x. You can see if you're looking for the x-intercepts on a graph, all of the y values for every point that lies on the x-intercept, the y-coordinate is 0. So therefore, if we set y equal to 0 and solve for x, we have found the x-intercepts. To find the y-intercept, we set x equal to 0 and we solve for y. That is because when I look at my y-axis, everywhere, every point that is on the y-axis has an x value that is 0. So therefore, if I make x equals 0 and I solve for y, I have found the y-intercept. So, in my first example, I'd like to find the x and y-intercepts of this following graph, if they exist. So, my function is y equals the opposite of the absolute value of x minus 2. So, to find the x-intercept, we set y equal to 0, and then we solve for x. So the first thing I did was I divided both sides by -1, and then I set what was inside equal to 0, and I found that x is equal to 2. So therefore, my x-intercept is 2, 0. My y-intercept I find by making x 0. So I put 0 in for x, and I solve for y. And I find that y is equal to -2. Therefore, my y-intercept is 0, -2. I'd like you to try finding the x and the y-intercepts of this graph if they exist. Press pause on your video. When you're ready to see the answer, press play. So as you can see, to find the x-intercept, I plugged in 0 for y. I plugged in 0 for y, and then I solved for x. I found that x was -2, so my x-intercept is -2, 0. To find the y-intercept, I plugged in 0 for y, and I solved for, I plugged in 0 for x, and I solved for y. Now you can see that y squared is equal to -2, and therefore there are no y-intercepts because we are dealing with real numbers. I'd like you to try this. When you're ready for the answer, press play again. So pause and then press play. Again, to find the y-intercept, we plug in 0 for x. So once I have that in there, I have 2 over -1, which gives me -2, and my y-intercept is 0, -2. To find the x-intercept, I plug in 0 for y, and I solve. So when I solve this equation right here, I multiply both sides by x minus 1, and I get 0 is not equal to 2. Well, I get 0 is equal to 2, which is just not ever true. So therefore, I have no x-intercepts. My y will never, there is no value of x for which my y will be 0. The next thing we'd like to talk about is symmetry. So it conveys balance, and symmetry gives us some information about the graph. So if I take a look, I can see I have 3 different graphs here. I have the one on the left, and you can see it's symmetric over the line, over the x-axis. It's the mirror image of itself over the x-axis. The second one is symmetric over the y-axis. It's the mirror image of itself over the y. So if I were to take this piece of paper and fold it in half, where my fold rested along the y-axis, it would lay right on top of itself. In the third graph, it's symmetric over the origin, meaning if I were to rotate my graph 180 degrees, it would land right on top of itself. So again, symmetric to the x-axis, symmetric to the y-axis, symmetric to the origin. Now, this is how you would test to see what your graph, what the symmetry is of your graph. So if you want to see if something is symmetric to the x-axis, you would plug in -b and see if it's on the graph. So if the point AB is on the graph, then the point A -b is on the graph. That's because for every A value, if it's symmetric over the x-axis, I have a point of the same distance above and the same distance below. So to test this, we replace y with -y. If it leaves my equation unchanged, then it's symmetric to the x-axis. I can tell if it's symmetric to the y-axis by looking at it this way. For every point that is on my graph, if it's symmetric to the y, here's a point A, B, then the point -A, B has to also be on my graph if it's symmetric over y. Same distance right, same distance left. So I can tell if it is symmetric to the y-axis by replacing x with negative x. If it leaves the equation unchanged, then it's symmetric to y. Now, if I want to test to see if my graph is symmetric to the origin, for every point AB on my graph, the point negative A, comma, negative B is on my graph. That's what would cause my graph to rotate 180 degrees. So I can tell if it's symmetric to the origin by replacing x with negative x and y with negative y. When I simplify, if the equation's unchanged, then it's symmetric with respect to the origin. So there are 5 possibilities for symmetry. There may be no symmetry. There may be symmetry with respect to the x-axis only. There may be symmetry with respect to the y-axis only. There may be symmetry with respect to the origin, or there may be symmetry with respect to the x-axis, y-axis, and the origin. So, how do you test for symmetry? So again, when I'm testing to see if it's symmetric over the x-axis, I put negative y in for y, and then I simplify. So if I put negative y in for y and I square it, I get just y squared equals x cubed. It looks the exact same as my equation, and therefore it's symmetric to the x-axis. To check to see if something is symmetric over the y-axis, I put negative x in for x, and then I simplify. Negative to the 3rd power is still negative, and this equation does not look like my initial equation. Therefore, it's not symmetric to the y-axis. When I look at the origin, in order to tell whether it's symmetric to the origin, I put negative y in for y and negative x in for x, and then I simplify. This negative y, when I square it, just becomes y squared. The negative x, when I cube it, the negative stays negative, and I have y squared equals negative x cubed, which is not the same as my original equation, so therefore it's not symmetric to the origin. I'd like you to try this one. Test to see if what the symmetry is. Press pause on your video. When you're ready to see the answer, press play. So this one is symmetric over the x-axis. When I put negative y in for y and I simplify it, it looks like the original equation. It's not symmetric to the y-axis. I put negative x in for x, not equal to the original equation. It's not symmetric to the origin either. If I put negative x in for x and I simplify, I don't get the original equation. So therefore, it is only symmetric over the x-axis. That concludes the lesson for today. Work on the assignment that is posted online. Have a nice day.